folks, welcome in. As you know, I haven't got my microphone yet, so if you cannot hear me clearly from the back of the room, please come a little bit forward. Hopefully I'll get my microphone very soon. Okay, and welcome in to 30A. If you're not in 30A, apparently there's like some administrative problem, but this is the 30A class, right? Okay, sounds good. And now we have our course announcement on Brewing Learn. I hope you can all see that. It's basically like how to get you familiar to our teaching style and to access the course material as efficient as possible. So this is our week 0. So as you already know, we don't have discussion session this week. I have uploaded my course syllabus. We will go over the course syllabus together today. And then I have several things that's more specific to this class. First of all, if you have any like general questions, whether it's administrative or it's a course-related question, it's encouraged if you post it on discussion board on Brewing Learn. So it's pretty straightforward to access it. You just like go to your Brewing Learn. There's a specific link, say like discussion. Just like go there and like ask for any kind of administrative questions you might have. If you have like privacy related question, of course you can email me, but it's more like a general question. Like if the lecture is recorded, where do I find the lecture recording? Those kind of questions, it's highly recommended ask it on our discussion board so your fellow classmate can also see it. I mean, there's no stupid question. If you are confused with something, it's probably my fault, and I want to make it as transparent as possible. And the same applies to our chapter relevant, material relevant questions, right? So if you are confused with a concept, it's much straightforward to post it on there, so your TA and I will answer it as soon as possible. And this way your fellow classmate who might be confused on the same topic can also see our reply. Right, so that's a general thing. I have also posted a syllabus quiz, basically like very straightforward questions for you to answer regarding our course syllabus that we will go over together right now. So do remember to take that syllabus quiz so you get that extra credit. Okay, so for our actual syllabus, here it is. There are several things. I'm just gonna go over it slowly. If you have any questions, just raise your hand or shout very loudly. Don't shout too often though. Okay, getting started. Well, this is Chem30A. I'm your professor. My name is Huiling Xiao. And my office is Yang Hall 2222F, so right outside the seminar room in Yang Hall. And I do have a semi-open door policy. So if you see me in my office and my door is open, you're welcome in to just ask like a general question or a quick checkup. That's totally fine. But if my door is closed, please allow me some concentration time if possible. I'll also host regular office hours every Tuesday. We can meet in my office, or I have also reserved the room 4222D1 for you to use during office hour. If there's like a department event going on and the room is no longer available, let me know and I'll try to find out some other rooms. And let's see. Well, then we have discussion sessions that are hosted by your TA. So depending on which section you're in, you might have different TAs. If you want to switch discussion sessions, do make sure you let your TA know ahead of time. We're generally okay with like people switching sessions between the same TA, but do let your TA know ahead of time to avoid any confusion. Okay. Course materials. We have 3 parts of our course material. One is your textbook, obviously. 2, I highly recommend you get a molecular kit. So that's the ball and stick that we will be using it to talk about what the structure of an organic molecule looks like. Note that you probably don't need like an entire molecular kit. It's totally fine with me if you share that kit with your classmates or anyone in the group you want to share, or just get some ball and stick. You don't need the entire kit. And the other thing is we will be using what we call the Bacon platform for extra credit items. So it's basically a free platform for you to get enrolled and get more practice problem. It's originally developed by Neil Garg, who was our department chair. And it's been proven to be pretty useful resources for you to have. I only use that for like extra credit, and I kept all the module open. You can access it whenever you like. But I mean, just use it. It's like a supporting material for you to use. Okay, and then to where you actually cares about our course policy. Right, so our course policy is pretty straightforward. You have 35% of your grade to be your discussion worksheet. So note that these discussion worksheets are your homeworks you do in your discussion session. You can discuss with your TA, you can discuss with your classmates. But do take advantage of these homework. Like I see enough example of people just don't submit their homework and mess up with their grade. Like don't do that, it's easy points. And then we have midterm exams and final exams. So I have some extra credit from Bacon, as I said. Pretty straightforward grading policy. And then for exam policy, so this might be slightly different. My background is physical organic chemistry. So I'm the kind of person who cares a lot about understanding of the reaction mechanism and do prediction, answer questions based on the reaction mechanism, AKA how does it take place, right? So my exams will be open book, open notes, meaning you can take anything on paper. I don't care how many pages you bring, or if you can bring your entire textbook, that's fine with me. But you cannot use anything on electronic devices. So that means in this class, please just focus on trying to understand what is behind all those organic reactions. No need to memorize everything. All right, so just focus on understanding of the course material. That's my total emphasis here. Regrade policy is pretty standard. We'll let you know once we have your midterm 1 exam. You have 3 days for your regrade, basically. And the letter grade policy is just your standard UCLA grading policy. Means like you receive 90% or more, you have some flavor of A, etc. For curving, so I don't curve like specific midterm exams. Let's say if your midterm 1 average is like 70%, I don't curve that specific exam. But what I do is at the end of the quarter, we look at your entire grade. So if our class average on the final total grade is below a B minus, then we'll curve everyone up so that our class average is at least a B minus. It will not work against you, meaning like if our class average is already A minus, well, I don't care, you earned it, right? So just to know, like I don't curve specific midterm exams, but we will have like a class average of B minus or higher at the end of the quarter. And everything else are pretty standard. If you have like exam kind of related question you want to discuss with me, it's more like a case by case scenario. And then we have our course schedule. It's basically in this quarter, we'll be talking about basics of organic chemistry. We'll start from the more boring part. What is an atom? What is a molecule? What is a chemical bond? How to draw organic molecules? What are the nomenclatures of organic molecules? And basic vocabulary is there, like what are functional groups? So chirality, acid-base, conformation analysis. So before midterm 1, basically we're learning vocabularies of organic chemistry. And then after midterm 1, we'll have 3 classes of reaction that we talk about. First big one is reaction with alkenes, and then reaction with alkynes, and reaction with haloalkenes. That's between midterm 1 to midterm 2. After midterm 2, we'll be talking about 2 specific types of reactions. That is the beta hydrogen elimination and your nucleophilic substitution reactions. SN1, SN2, E1, E2. You might already learn this term. So I'm going along the chapters in your textbook. Basically, we start from chapter 1, we end in chapter 9. So very standard. One thing I do want to mention is next Friday, I will be traveling for a conference. So there will be a guest lecture by Professor Rajat Mash. He's also a good organic chemist in our department. He'll take good care of you. Okay, let's see. Any questions before we start? Yes?
Will the lectures be recorded?
Yes, I am recording it right now. So regarding that, two things really. First, I will record everything. Basically, I'm recording it on my iPad. So if I'm writing on my iPad, you'll see like how we do it. But please be noted, like there are cases I will be writing on the board. So you shouldn't be using that recording as like a perfect substitution of coming to class. But I'll try to post it as soon as possible. Anything else? Or if you, yeah.
How are your midterms evaluated?
I'll post my my previous midterm exam, or I'll have more information when we actually come to there. It's likely to be a mixture of like some multiple choice, some short answer, and some comprehensive problems. Yes.
Just out of curiosity, with discussion assignments, like past courses, it's graded on accuracy, right?
Yes. The discussion worksheet will be graded on accuracy. Yeah, and if you have those kind of questions later on, feel free to just post it on Bruinler. We'll answer it as soon as possible. I'll also be in my office for the entire afternoon today, so feel free to stop by if you have anything that come to your mind after today. Okay, sounds good. So let's get started in organic chemistry. All right. So we will spend 3 lectures, that is today, next Monday, and next Wednesday, basically reviews, right? So we're trying to refresh your memory on 2 things. What is an atom and what is a chemical bond? So today we'll be focusing on the atomic structure review, say what is an atom, and then we'll start from there and talking about the classical bonding theory. So that involves Lewis dot structure, functional group nomenclature, like what is a keton, what is an aldehyde, VSEPR, and how do we describe shapes of a molecule, and then resonance structures. And later on, we'll also talk about some quantum mechanical bonding theories, because after all, from the microscopic point of view, we know that we need to describe like molecules and atoms using quantum mechanics. So we want to introduce you to the more slightly advanced quantum mechanical bonding theories. So getting started, atomic structures. So back to general chemistry. Right now, you should be knowing, like, for when we're describing microscopic objects, we need to use quantum mechanics. The fundamental equation for quantum mechanics is you have some kind of Hamiltonian operator acting on a Schrödinger wave function that gives you the eigenvalue of that Hamiltonian times the wave function itself. Or the other way to put it is by solving the Schrödinger equation, we get a wave function, say as a function of x, y, and z, which are positions of the microscopic particles that we care, and also time. So what is a wave function? So effectively, the wave function phi, or the Schrödinger wave function, it's like an oracle. If you watch old movie like Matrix, basically you ask the oracle question. So the way you ask the oracle is like, oh, I want to get energy out. So you want to use the correct operator to get the energy. So in this case, we'll be using like Hamiltonian operator, acting on your wave function to get energy times the wave function. And what if I want like probability? What's the probability of finding an electron in somewhere in space? Right, so you do that probability equals to absolute value of your wave function squared. And by the way, I post my annotated notes on all my lectures, so don't worry if you like didn't write down everything. So the short take-home message here is that the wave function gives you information about energy, position, probability of a given microscopic particle. We can solve the Schrodinger equation, so the H phi times E phi, for any one electron systems, like hydrogen, helium plus, or lithium 2 plus. And these exact one electron wave function are our atomic orbitals. All right, so atomic orbitals are effectively just your Schrodinger wave function you can solve for hydrogen. We'll revisit the concept of atomic orbital later on when we start talking about quantum bonding theory. For now, we want to quickly refresh your memory on what these atomic orbitals mean. Like when we say like atomic orbitals, we have different quantum number to describe these atomic orbitals. Remember, atomic orbitals are just wave functions. So for different states, you have like different wave functions, different atomic orbitals. So we have basically three quantum number that we care about as chemists. You have the principal quantum number, so that is n, that's positive integer numbers, 1, 2, and 3. That tells us, the principal quantum number tells us the quantized energy level. All right, so remember our oracle example. It's like asking the oracle, what is the energy of my system? And the oracle tells you the energy of your system is quantized. So if your principal quantum number n equals to 1, you have the negative z squared over n squared in unit of Rydberg. And z is your atomic number. And then we have our angular momentum quantum number. That is your, tells you the shape of your atomic orbitals. Basically, L, angular momentum quantum number, that tells you how many angular nodes you have in your atomic orbitals. In chemistry, we typically write like conventional name for these angular quantum number. So if you look at the allowed value of the quantum, the angular momentum quantum number, that starts from 0, 1, 2, all the way to n minus 1. So for example, if your n equals to 3, then your L, or the angular momentum quantum number, can take three different values. So your L can equal to 0, 1, or 2. All right, so these are the allowed value of your angular momentum quantum number. And in chemistry, again, we have conventional names for these different angular momentum quantum number. We can have L equals to 0. That tells us we have a s atomic orbital. L equals to 1 gives us a p orbital. And L equals to 2 gives you d orbitals. So one of the simple questions you can ask yourself is why there doesn't exist, say, a 1p orbital, right? Because when n equals to 1, the only value your L can take is 0, which reflects a s orbital. And then we have our magnetic quantum number. So that tells us these are the direction of your atomic orbital. It also tells us how many of those orbitals are allowed, right? So if you look at the allowed value for our magnetic quantum number, that's from negative L all the way to L. So it can be negative L plus 1, all the way to L plus 1 and L. So if you think about p orbitals, for example, when we say it is a p atomic orbital, we're saying that its angular momentum quantum number L equals to 1, right? So L equals to 1. And then for L equals to 1, how many possible magnetic quantum number we can take? So it can be negative 1, 0, or 1. So that's why we only have 3 p atomic orbitals. Yes.
Should not be L minus one.
Which one?
It's the one before L.
This one?
So like N equals negative L.
This one is negative L.
Yeah, but negative L plus one. And then this.
Oh, it is negative L plus 1 if you think about
Yeah,
it.
the next one should be L minus one.
Oh, this one? Oh, yeah, this. Okay, thank you for pointing that out. Can you also post that on the discussion board so I know I need to update my notes? All right, and now it's a good timing for us to review what these orbitals look like. Well, again, use it in our quantum bonding theory section. So 1s, what does 1s mean? 1s means my principal quantum number n equals to 1, my angular momentum quantum number L equals to 0. So we have 0 angular node. So a node plane, again, refresh your memory on that. A node plane is when your wave function changes phases. So it has like the shaded versus the unshaded area. So in this case, for our 1s, it's just a spherical orbital. It's either all shaded or either all unshaded. And for our 2p atomic orbitals, this means we have n equals to 2, L equals to 1, and you have 3 different p orbitals. Each of them have 1 angular node. So if we define our Cartesian coordinate like this, well, I can copy paste it down. So this one will be my PZ. Along the y-axis. Well, actually, let me draw it in a different figure. That's my 2py. And then you have the 2px. All right. And when we say a node plane, it's whenever we have change of these signs of your wave function. So these are your node planes. And what does it mean by node plane? Again, remember, we're talking about a wave function, which is why these atomic orbitals are effectively your Schrodinger wave function, right? So these are your Schrodinger wave function as a function of x, y, and z. And the probability of finding the electron in space is phi squared. So what does it mean? It means like if we have less drawing, around the node plane, we have less probability of finding the electron closer to the node plane. All right, so refresh your memory. What does these terms mean? What's the physical meaning of these terms? And now with these atomic orbitals, again, we have the combination of the first 3 quantum number gives you the name of our atomic orbitals, like what we just did, right? So a 2p atomic orbital will have n equals to 2, L equals to 1. All right. And now we have all these orbitals. We're ready to pop electrons into these atomic orbitals. So this is a common misunderstanding I want to refresh again. So atomic orbitals are just mathematical functions. They will exist whether or not there's an electron in there or not. These are just wave functions. But depending on what exactly is your system, these atomic orbitals may or may not be occupied. And that's where electron configuration comes in. So electron configuration is pretty much just rules to follow. So you're assigning electrons into different atomic orbitals. Okay. And let's look at these 2 rules, right? So first of all, these 3 rules actually. First of all, the lower energy atomic orbitals will be filled before the higher energy atomic orbitals. So you start from bottom up, right? So remember when we say the principal quantum number, which is your principal quantum number n. So the smaller principal quantum number, the lower the energy will become. Right? So the atomic orbital with smaller principal quantum number will get filled first. And when you fill it in, well, no two electrons in the single atom can have the same set of all four quantum number. So what does that mean? We already talked about N, L, and M. Remember, these are description of your atomic orbitals. And then we have the spin, right? So for electron, you can have either spin up or spin down. Or MS can take like plus minus 1/2 value for electrons. So that's why each atomic orbital can take up to 2 electrons. And these 2 electrons must have different spin. And again, what is spin, right? Spin is basically how your electron responds when an uneven magnetic field is applied to that electron. And that's part of the reason why NMR spectroscopy is working. And then at the last, we have our Hund rule. So basically that's when electrons enter degenerated atomic orbitals. So degenerated means atomic orbitals of the same energy. And each electron will enter the atomic orbital before they start to pair up with each other. And let's look at 2 examples together on the actual energy level diagram. And what do we mean when we say like, hey, write me the electron configuration of something? So for carbon and oxygen, we can imagine to have like one s orbital to be lower in energy than your 2s, than your 2p. So for carbon, well, we have z equals to 6, which is your atomic number equals to 6, meaning we have, for a neutral carbon, you have 6 electrons you need to fill in. And the 3 rules we're following, we start from bottom up. So 1, 2, 3, 4, 5, 6. And these p orbitals are called degenerated with the same energy. So when we write out the electron configuration of your neutral carbon, it is, well, 1s2, 2s2, 2 electrons in 2s orbital, and 2p2. Or alternatively, we can use the noble gas notion. So in this case, that's helium, 2s2, 2p2. Because helium will have the electron configuration of 1s2. And same applies to, say, oxygen. Now for oxygen, we have z equals to 8. So we have 8 electrons we want to put in. Let's be 1, 2, 3, 4, 5, 6, 7, 8. And your oxygen electron configuration is 1s2, 2s2, 2p4. Or alternatively, you can write it as helium, 2s2, 2p4. Okay, how are we doing so far? Works yet? Let me know if you have any questions on this topic before we move on to talk about classical bonding theory. Good? Okay, sounds good. Okay, now classical bonding theory. This should also serve as a refreshment of your memory. We just talked about the atomic structure, which is the actual correct version of what electrons are, right? So they are not pure particles. But in classical mechanics or in classical bonding theory, we're not using quantum mechanics in this classical bonding theory part. We're gonna roll back to like 100 years from now and think about like what are chemical bond in the classical picture of electrons behaving as pure particles. Now, it is not correct. It's not technically speaking correct. But, well, these models are super useful in organic chemistry. That's why we're still using them. But just keep in mind the actual chemical bond need to be described using quantum mechanics. But we will be using these classical bonding theory in organic chemistry as well. So all models are wrong, some are useful. So in classical bonding theory, we're effectively treating nuclei and electrons as pure charged particles. So your nuclei is +1 charge, or plus Z charged. Your electrons are always negatively 1 charged particles. And then before we start talking about bonding, we need to talk about the concept of electron negativity. Basically, it's a measure of an atom's ability to attract the electrons that is shared in a chemical bond with another atom. So in this case, when we're talking about electron negative atom, for example, like fluorine, we're talking about fluorine being able to attract more electrons to its core. And then the electron positive atoms will be like further away. Comparing to fluorine, everything is electron positive. So we're looking at maybe like sodium or like carbon. These are like more relative electron positive atom comparing to fluorine. The easiest way to, get an idea about the electron negativity of an atom is either you check a table or from the periodic table, just remember your fluorine is always the most electron negative one. So just draw a line directly towards fluorine. You will have situations where the two atoms have very similar electron negativity, like maybe in carbon and then in hydrogen. And these, if they have like similar electron negativity, that's also okay. And they will contribute to polar versus nonpolar covalent bond that we will discuss later on. All right, so with the concept of electron negativity, we're ready to move on to talk about types of chemical bonds. So depending on how big the electron negativity differences are between these atoms, you can have, ionic bond, covalent bond, or non-covalent. Within covalent bond, you can have non-polar covalent bond versus polar covalent bonds. So let's look at the ionic bond first, right? So when we say ionic bond, we're saying the electrons between, the electron negativity between the two atoms that form a bond is super different. So the entire electron is being transferred to the more electron negative atom, right? So typical examples like sodium chloride, right? So sodium is a very electron positive atom, as we can see. And then chlorine, on the other hand, is on the other end. It's an electron negative atom. So in this case, the electron in sodium is being completely transferred into chlorine. And the result comes to form a sodium plus, which is a cation, with the electron configuration of neon. And then we're forming chlorine anion, which has the electron configuration of argon. So in both cases, we're forming, so for these cases, they're charged, right? But we're forming the stable noble gas configuration. And then we have covalent bonds. So when we have atoms now have comparable electron negativity, like maybe between carbon and hydrogen, between phosphorus and nitrogen, etc. So, or between carbon and fluorine, right? They have different electron negativity, but still relatively comparable. We're not going across the entire periodic table. And then we have covalent bonds. So in covalent bond, instead of entire transfer of the electron from one atom to the other, we have electron pairs being shared between the two atoms of interest. So what does that mean? So if we look at the actual graphic representation of a covalent bond, we have two different types, remember. One is the covalent bond between two atoms of similar electron negativity. So the force analysis is very straightforward. Remember, we're only using classical mechanics here. So just electrostatic repulsion. Whenever you have, let's say, a H2, imagine the H2 here, the nucleus of the H2 will be repulsive to each other because they're both positively charged. However, the electrons, which is negatively charged, will act more or less as a glue to hold your nuclei together, so you form a covalent chemical bond. Right? So the electron pairs acting as a glue to hold the two atomic nuclei close to each other. So in a nonpolar covalent bond, the electron negativity is similar or equal. In this case, it's a bimolecular. Then the electrons will locate right in the middle. It's equally shared between two atoms. So that becomes a nonpolar covalent bond. Alternatively, we can have polar covalent bonds. So when we say a polar covalent bond, let's say HF as another example. So HF will have a larger differences in electron negativity. So fluorine is more electron negative, hence the electron pair will be attracted closer to fluorine. And that creates a partial charge separation. And if we look at the actual representation of a polar covalent bond, we use dipole moment to describe it. So you'll see this often. On the left, we have the more electron positive hydrogen. On the right, we have the more electron negative fluorine. Right? So the electron will be shared more closely to fluorine. And this creates a dipole moment. So we draw the dipole moment from the partial positive charge to the partial negative charge. Now, the dipole moment of this chemical bond can be affected by multiple reasons. We just said one, which is the electron negativity of the two atoms. The dipole moment itself, as an electrostatic using Coulomb's law, is also sensitive to the distance between the two atoms. It is also affected by the polarizability of the atoms. We'll talk more about it when we talk about haloalkanes and also the trend of the dipole moment in those polar covalent bonds. But for now, I do expect you to know, like when you have a covalent bond, you'll be able to tell whether or not it is polar. If it is polar, in which direction does the dipole moment point to? Am I out of time? Sorry, 1 second. I can't see time on my iPad right now. Okay. Well, we have 15 more minutes. Okay. All right. So that's the dipole moment. And now we're ready to move on to Lewis structures. Any questions before we move on to Lewis structures? Yes?
I'm sorry, was it for the polar bond where the electron has a tendency to move towards one side versus?
Right. So for polar covalent bonds, we have like two atoms with different electron negativity, right? So remember, the more electron negative atom will have a stronger force to attract the electrons to them. So hence, we're building up a partial negative charge coming from the electron pairs and on the electron negative atom, and a partial positive charge on the left-hand side because of the uneven shared electron pairs. Yes? Right, so for the node plans, so if you think about what is a node plan, so the node plan concept itself is telling us at the node plan, if you think about the actual wave function, like a sine wave, right, so you have something like this, right? So at the node plan, my wave function, phi, is actually at 0, all right? So when my phi is 0, then the phi square is obviously 0. So at the node plan, you have less probability of finding that electron. And that's what we're saying when we're saying there's low electron density at the node plan. So in this case, what's the take-home message we will learn later on is when you have two orbitals and they're interacting with each other, they must be interacting through these lobes. At the node plan, there will be no interaction at all. Okay, let's see. Lewis structures. Well, so these basically, again, it's a review. It's how we draw molecules in organic chemistry. Right, so there are several terminologies we use in Lewis structure, saying like what is valency. So valency basically say how many unpaired electrons are there by looking at the periodic table. So you can have monovalent. So if we look at the period 2, and let's write out what are the elements that's like monovalent, divalent, trivalent, or tetravalent. So what are the monovalent? Like one unpaired electron. Then we're looking at lithium and chlorine. For divalent, we're looking at 2 unpaired electrons. So that's beryllium and also oxygen. Whoa, sulfur. Wait, it's oxygen, sorry. And this should be fluorine. Right, and trivalent, that's going to be my boron and nitrogen. And then carbon is the tetravalent species. And in classical bonding theory, each of these unpaired electrons can form a chemical bond. So that's why in classical bonding theory, carbon is like 4 bonds because it's tetravalent, has 4 unpaired electrons, ready to form covalent bonds. That's the first rule, valency. Second rule, octet rule. So octet rule is typically true. So let's just assume the octet rule is true. What does it mean? It means hydrogen wants 2 electrons to have the noble gas configuration of helium. P block elements, so your boron, carbon, nitrogen, oxygen, etc., they want to have 8 electrons in their atomic orbital to fitting the noble gas configuration. And when the electron pairs is shared, it's basically you count that electron pair for both atoms. So that means we have this octet rule. So the number of shared electron pairs in a molecule, or the number of covalent bonds in a molecule, is 1/2 times 2 times the number of hydrogen, and 8 times the number of p atoms. So you can call this like octet fantasy. Right, so that's what all atoms want. And you want to minus the number of valence electron available. So that's your sad reality. So when drawing the Lewis dot diagram, it's always helpful. You start from like, okay, thinking about how many covalent bonds are there in this molecule. So let's look at an example together. I'm just copy paste down this one here and say like use the octet rule to solve for the total number of covalent bonds in NH3. It's pretty straightforward, right? It's just 1/2 times, 2 times the number of hydrogen, which is 3, plus 8 times the number of p atom, which in this case we only have 1 nitrogen, that's 1, minus the reality, right? So hydrogen itself only have 1 unpaired electron. Nitrogen have 5 unpaired valence electrons. And you do the calculation, you get it to be 3. And by the way, this is a level of calculation we will do in this class. So for exams, if you have a calculator, bring it. If not, it's probably fine. All right, so don't ask me what kind of calculator you can bring. Okay, and now we're ready to draw the actual Lewis dot structure from the calculated octet rule. You have nitrogen in the center, and then it will form a covalent bond with each of the hydrogen. And then we have a lone pair. And you can check whether or not it's fitting the octet rule, right? So surrounding the nitrogen, we have 6 electrons in set 3 bond and 1 lone pair. And then in each hydrogen, we have 2 electrons. Octet rule is also applicable to double bond and triple bond. Like a double bond is basically counting as 2 covalent bonds. A triple bond is counting as 3 covalent bonds. So in the example of, say, acetylene, right, so we have CH 2H2 as our molecule. Now, using the octet rule, the number of covalent bond is 1/2 times, well, 2 times 1, that's the, 2 times 2, that's the 2 hydrogen we have, plus 8 times 2, that's the 2 carbons we have, and minus the actual reality. We have 4 carbon, we have like 2 hydrogen. We have 4 carbon, and each carbon have 4 valence electrons times 2, and minus 2 electrons in each hydrogen. You do the calculation, you're like 1/2 times 4 plus 16 minus 8 minus 2, and that gives you 20 minus 2. We're looking at 5. So where are those covalent bonds, right? So your carbon and hydrogen can only make 1 covalent bond with each other. So first writing the hydrogen, and then we need 2 more covalent bonds, and that's why it's a triple bond. And at the end, we also have the concept of formal charge. So formal charge is after we fill in these drawing, and you count the number of electrons by breaking the bond evenly, like how many electrons are surrounding each atom. So in this case, the formal charge on each atom equals to the number of valence electrons minus the number of lone pair electrons and minus the number of 1/2 times the electrons in a chemical bond. So if we look at carbon monoxide, using the octet rule, the number of covalent bonds we have must be 1/2 times 2 times 8 times 2. So we have 2 p block elements, minus 4 from carbon, minus 6 from oxygen. That gives me, well, 2 times 8, 16, minus 10. And that's 3. So we must have a triple bond between your carbon and oxygen. So when you draw out the Lewis dot diagram, what we have is carbon triple bonded to oxygen. Note that triple bond comes from the octet rule. We must have that triple bond so that your each atom will have a lone pair around it. And now you count the formal charge, right? So if we cut this bond in middle, it becomes 3 electrons, and the carbon now have 5 electrons surrounding it. So that's why we say it's formally a negative charge. So carbon will have a formal -1, and oxygen will have a formal +1, because it has 1 less electron than its neutral form. And then as a summary, we have different steps to draw like valid Lewis dot diagrams. That's like determining the number of valence electrons, determining the arrangement of atoms. This typically means you put the least electron negative atom as your center atom. Then you connect the atoms by single bond and add a double bond if needed, and then arrange the remaining electrons so everything have like a full valence shell. So 2 for hydrogen, 8 for p block elements. And then at very end, check for formal charges to make sure they're accurate. And am I running out of time? Okay, I have 3 more minutes left. So let's just do one more quick thing, which is the violation of the octet rule. So octet rule is typically working. Remember, that's the counting the number of electrons available. It's basically 3 scenarios we can violate a octet rule. One is we simply do not have enough electrons. So that happens when we have the metal hydride, right? So lithium hydride, or like BH3. You simply do not have enough electrons. Second time, you can have valence shell expansion of period 3+ element. Or for organic chemistry, it's always the case. It's pretty much always the case, like whenever you have a center atom as phosphorus or sulfur, keep in mind they can violate the octet rule. Meaning like in SO4, if we draw out the Lewis dot diagram to satisfy all the oxygen, we will have sulfur breaking the octet rule. And at the end, when you have like odd number of electrons, like free radicals, for example, NO, so your nitrogen have 5 valence electrons, your oxygen have 6. So inevitably, you will have like an odd number in your valence electron. And that's also a violation of the octet rule. And that's about it, right? So basically today we go over like basically we're refreshing your memory in previous knowledge in like atomic structures and classical bonding theories. And that's it from me today.